Okay, so the title of my talk is quite broad, I have to admit. The role of glycosylation in IgG Fc receptor interactions. I will highlight a few aspects of that. It's going to cover some technology, but also some clinical applications and some, actually 2 clinical applications. Let's see. Firstly, about where we are. So I'm not at the RA department, same hospital. So this is the building where René and Tom are also with their department. But I'm really in a tech department, which I'm leading. And we're developing technology and using them to address clinical questions, mainly mass spectrometry with separation sciences. And my specialty is then on glycoanalytics. And so I chose 3 subjects for this morning. The first one is more on technology to resolve these glycoforms, how they interact with the Fc receptor. So why does the one glycoform interact better than another one, and how can you measure that? Then the next aspect is measuring glycosylation, but not only glycosylation, measuring it in the context of other modifications, allotypes, subclasses, all of that. And the last aspect is more looking into clinical application, and that's going to be transplantation of kidneys. Now let's start with the Fc receptor interaction with antibodies. This is glycoform dictated. We heard that in several talks already by Falk, but also by René. So we have all the glycoforms, and then we have a range of Fc receptors. And my talk will now be on technology to resolve which of these different glycoforms of an antibody is now interacting better or less good with a receptor. I think the aspect that a co-fucose is relevant for the interaction has been highlighted abundantly already, but these are really old findings showing that indeed presence or absence of a fucose matters in cytotoxicity assays in vitro, and we have a molecular understanding of how this matters. So you can here see fucosylated Fc portions interacting with a 3A receptor, so in the crystal structure, and you can see how the presence of the fucose affects the interaction and disrupts hydrogen bonds, and by that affects the affinity. And so if you want to dissect this and look at all these different glycoforms, this is an approach which Gesto Vidason, our collaborator, took some 8 years ago, and this involved production of all the different variants of the antibody one by one. So it's glycoengineering. You think about which enzymes you want to use, you come with inhibitors, and you engineer all the glycosylation, you produce all these you produce all these variants of a monoclonal antibody, and then you probe them in a binding assay with a 3A receptor, as shown here. You can also use it in vitro cellular assays, and by that you get a very differentiated picture, highlighting that indeed the variants lacking the fucose are active, so those are engaging with the 3A receptor. And the variants having a fucose on are virtually inactive and hardly bind to the 3A receptor. And as I said, the binding assay and then also the cellular assays are very much aligned. So this is the data you generate by conventional ways by producing all the glycoforms one by one. And this is then an approach which we pioneered some years ago. What we do here, and what is a different concept, is we produce we probe an antibody which is heterogeneous in glycosylation. So all the different forms are there. It's a wild-type antibody. This is a monoclonal. And then we probe the interaction with the Fc receptor by immobilizing the Fc receptor on a column. So the 3A receptor is immobilized on an HPLC column. We flush the antibody across the column, and then you have the binding in this HPLC column. And what we see is that some glycoforms have a very good binding. So those are the late-eluding ones. Those are also the ones lacking the co-fucose. So that fits with our expectation. And the forms which have fucosylation on both arms of the Fc portion are hardly interacting and elude early from this column. So this is an approach resolving, using mass spectrometry, all these different glycoforms, and actually the elution position tells us something about the affinity gradient of these glycoforms across the 3A receptor. Now, what we did a couple of years ago is we complemented this affinity LC approach with another approach, and I have a simple animation for this. So this is the affinity LC approach. We have a binding of the antibody to the LC column, and then we come with a pH gradient, and by that we step by step elute the antibodies according to their interaction strength with the column. Now, what we set up now alternatively is a CE approach, and we have Andras here in the audience, but also Erdmann, so some CE experts. So what we did here is we again used the mass spec to resolve all the proteoforms, but now we have an in-solution interaction of the antibody with the receptor. We have a microcapillary where this interaction takes place, and what we now resolve is some forms of the antibody interact better and others less good with the Fc receptor, so more or less interaction, and that results in a separation of these glycoforms in the capillary. And again, we use mass spec for detection. Now, these are the patterns we would get then. We do the experiment in two ways. We first apply an antibody to the capillary, do the separation without the receptor, so no resolution of the glycoforms. That's the upper panel. And now we titrate in the receptor into the capillary, and by that we enable the interaction of the receptor with the antibody, and that results in this resolution. And what we now see is some glycoforms only undergo a minor shift and others undergo a major shifts. So the ones eluting late are the high affinity variants. So again, we resolve according to affinity of this antibody to the 3A receptor. And a nice way of comparing the results here is just superimposing or having them next to each other, as shown here. So we have the affinity LC separation indicated here. We have the affinity LC and CE separation next to each other. We get virtually identical patterns. So we see indeed having the receptor immobilized, but also having it in solution in the capillary. In both cases allows us to separate glycoforms and resolve which of the glycoforms are binding more strongly or less good to the receptor. Now, another level of complexity is next to glycosylation, different allotypes and subclasses of antibodies. And this is now indicated here. So what we can do is have 4 different monoclonals, and we can now compare different subclasses of these monoclonals in their binding to different receptors. I don't want to go into detail, but a strength of this is that you're now not comparing different assays to each other, but it's in a single assay, all these 4 monoclonal variants or subclass variants of a monoclonal are together. They are competing for receptor interactions, and you really resolve them. How are they performing in terms of interaction with, for example, receptor 2A, a certain variant of the receptor, or a 2B receptor. And we now can quantify the shifts we observe by inclusion of the receptor, and these bars here indicate the strength of the interaction of a certain subclass with a certain receptor. So this was on resolving indeed proteoforms of antibodies for interactions with receptors, and you could also do this with lectins. You could maybe chip in DC sign instead of a 2A or 2B receptor, just to give you an indication that we have these capacities using mass spec and avoiding kind of the glycoengineering approach for probing these interactions. Now, this also stimulated us to say, okay, we want to have a method which allows us to look at the Fc receptor, at the Fc portion of an antibody, because of this Fc portion undergoes various interactions. We don't want to only look at glycosylation, we want to look at the entire Fc portion and assess how classes, subclasses, allotypes, glycoforms, and other modifications, all of them matter for interaction with all these target molecules. And for that, you have to be able to measure these Fc proteoforms or the Fc status. What we do for this is is we cut off using an enzyme the Fc portion from antibodies, and then we do this for polyclonals, and we start resolving all these different subclasses or allotypes. And here we have a homozygous donor having only one allotype per subclass. Here we have a heterozygous schematically indicated, and we can resolve all these Fc half portions. Just some technicalities. So why do we separate? We separate because many of these Fc halves have a very similar mass, so we need the resolution on the column to be able to differentiate these different Fc half proteoforms. Now, this is the pattern we get for one polyclonal sample, and you see that we get different subclasses and different allotypes. And for one donor, this is a more homozygous donor. The pattern is complex, but it gets, of course, more complex if you have heterozygosity. We then can quantify all these antibody patterns. We can look in an allotype-specific form, but also integrate different allotypes of one subclass, and that's indicated here, just assessing for this pool of antibodies, what is the subclass, what is the allotype profile. Now, we have other levels of heterogeneity in these samples. So we can look at glycosylation, obviously. So here I show the pattern for IgG1, and you can, next to assessing the allotype and the subclass, now resolve all the different glycoforms you have for the Fc half portion. For IgG1, this is not that complex, but if we look at IgG3, for example, there we have the aspect of macro heterogeneity. So we have the phenomenon that we have a non-glycosylated Fc half at minor levels. We have a monoglycosylated, but also two diglycosylated. So there's a second N-glycosylation site in the Fc portion of IgG3, often ignored. So we can assess this heterogeneity in terms of site occupancy, and we can then look per site how the heterogeneity looks like. So we can have the monoglycosylated and diglycosylated dissected and really look at the levels of glycosylation and silylation. So quite a level of detail you get on for these Fc portions if you use mass spectrometry for assessment. Now, we had this in place, and we then said, okay, we can now measure glycosylation, but we also want to look at other modifications. And one being that we have proteoforms like protein modifications. In this case, we have some forms which have a mass shift, not caused by glycosylation, but we guess either by citrullination or deamidation. So we have a range of other modifications which possibly interplay with glycosylation in modulating receptor interactions. And this is just ongoing. So we now have this method resolving indeed allotypes, subclasses, glycosylation, but also other PTMs. What we have done is use this now in collaboration with René and with Tom, and we looked at autoantibodies, these ACPA autoantibodies in RA. So we isolate the antibodies, we cleave off the Fc halves, and we measure them with the approach I just introduced. We do that next to analyzing the bulk antibodies, and we get then these profiles with a subclass and allotype information. We do that for different biofluids, so for plasma, but also for the site of inflammation, so for the synovial fluid. Because there you could maybe have other antibody repertoires being produced, and that's indeed what we see. We see that for bulk IgG, but we also see for these specific autoantibodies that we get certain subclasses and allotypes which are dominating. We do that for different donors. So this donor is way more heterogeneous, as you can see. So we see here that other subclasses and allotypes are chipping in already in plasma, but also for the specific responses of the autoantibodies in the synovium. So what we also cover is then the glycosylation. So here we have then the glycosylation profiles for measured for serum and for synovial fluid, or plasma and synovial fluid. And what we observe is indeed that glycosylation is different. So we have this very classical difference in glycosylation with a low level of galactosylation found for the synovial fluid as compared to plasma. So at the site of inflammation, we have this more inflammatory, phenotypically inflammatory glycoprofile with low levels of galactosylation found. Okay, so the take-home message I wanted to give in this part is simply that there is a history of studies which look at aspects like glycosylation, like oxidation, different modifications of antibodies. And historically, I would say that people choose their favorite modification, claim that they are only looking at that, and link that modification to a biological function. And I think we should move from there to assessing in a holistic manner what is the Fc portion of our antibody, look at allotypes, subclasses, and glycosylation, all the other modifications, and really try to assess how those modifications could interplay in steering certain effector functions. And I would have a short last part of my talk, and that's on kidney transplantation. So in this case, what we have done is we collaborated with Margaret Ackerman in Dartmouth, and she was wondering, in kidney transplantation, you have anti-HLA antibodies. So these antibodies may cause antibody-mediated rejection, so kidney rejection. These antibodies are against HLA molecules in the kidney and produced by the recipient of the kidney. And what we were finding is that we have afucosylation on some of these alloantibodies. And if you have more of the afucosylation, you have more of the rejection. And we also did some more functional studies, or they did functional studies, seeing that indeed the 3A receptor is implicated in this. This is just a workflow using bead immobilized antigens for purification of these alloantibodies. And then mass spec as a readout. And if you look at this, we now compare the glycoprofiles of total antibodies and of these specific antibodies, and then we see some afucosylated species popping up like the species here. So indeed, for some of these alloantibody repertoires, we saw that we have afucosylated responses. Now, this is simply the comparison of the total and the alloantibodies, and we see that indeed the anti-HLA A2 alloantibodies come with a lower fucosylation as compared to the bulk antibodies. Now, if you split this up into the patients which have complications, antibody-mediated rejection versus the ones which do not have the complication, then it's becoming really interesting. So we see that those patients with the complications, patients who would lose or at least get rejection complications, lose their kidney, come with a lower fucosylation on their alloantibodies. And that's again resolved here. So we have patients with rejection and patients without rejections, and those with a low fucosylation or a medium level of fucosylation are the ones having a rejection as indicated by the red bars here. So these are low numbers of patients, but we think this is a interesting direction, and we're teaming now up with kidney transplantation physicians and see whether this could be an additional marker, because we have to say the levels of these anti-HLA antibodies are rather poor predictors of complications, and we are assessing whether looking at glycosylation could be an additional layer which allows to predict complications in kidney transplantation. Just a bit more on the characterization of these alloantibodies, I have to say. So this is binding assays to the 3A receptor, and what Margaret showed here is indeed for the antibodies which have a high fucosylation, we have a high off rate from the 3A receptor, while the antibodies which are afucosylated, they stick way longer on the receptor. So off rate seems to be a major differentiation factor, or it's the factor how the high affinity is being reflected in these alloantibodies. Now, conclusions. So we have these afucosylated antibodies, and we think those are linked to rejection in kidney transplantation. And we see also they have different molecular behavior as reflected in their higher affinity to the receptor, but also in the reduced off rate from the 3A receptor. And so these alloantibodies may indeed cause kidney damage by recruiting immune cells. And so what we want to do is follow up on this. So we want to see early on, when you have these alloantibodies, do they already have this low fucosylation, or is this something which is just emerging in the course of kidney complications? And we want to see whether this could be a marker for patient differentiation upfront upfront of the kidney transplantation. Okay, just maybe 2 slides on a broadening of our glycoanalytical platform. So Fc glycosylation is important for a lot of effector functions. And what I want to show here is, indeed, we have the wealth of different glycosylation sites on different antibody classes and subclasses. And I just wanted to indicate that we have also the ambition of not only sticking to IgG, but because other subclasses and other classes are also likely important, although less studied. So we now plan to expand our platform to measuring also IgA variants like IgA1, IgA2, assess all the different glycosylation sites on those molecules, also including IgM. So really have a more holistic way of profiling, let's say, autoantibodies and assessing their modifications in the Fc portion. And this is looking already quite promising. So we have now this integrated platform to look at IgG, IgA, and IgM glycosylation by mass spec. So this is the team which has been working on it a lot. So our CPM, so tech department at LUMC. And I want to acknowledge collaborators. So again, a lot of team members. Norje, Konstantin, Tamas did a lot of the work, but also Elena, Christoph, and so on. We work a lot with the RA department, with Gesto Widerson from Sanquin, with Roche for characterization of biopharma samples, and I want to acknowledge our funders. Thanks.